Welcome to October 2nd, Wednesday SI. Tom here at 11:12 p.m. on a Sunday night doing organic chemistry for you. All right. I also get paid to do this, so multiple modes of motivation there. Okay. I'm sticking to what's on the schedule for Wednesday's class. Usually we'd have SI right after class on Wednesday. I'm going to be gone then, so supplemental video today. Again, like the last video, this one's probably going to be shorter than that one. Kind of go over some problems, pause the video, try the problems on your own. Even if you get them wrong, that's okay. Still better to try them on your own and catch your mistakes. That way, come assessment time, you can catch those mistakes again, okay? Another method would be watch the video, watch the video straight through, go back to the beginning, try the problems on your own, and yeah. Most of these are coming from the textbook, so just sticking to the readings for Wednesday's class. I think it was only 3 or 4 sections. So again, it's going to be a shorter video, hopefully. I tend to yap when talk about organic chemistry. So, all right. I have 4 molecules up here, okay? And this is going to be a review probably from Monday's class of identifying chiral centers, okay? So remember those chiral centers, we need 4 distinct groups on a carbon. Boom, you got a chiral center, okay? Before we get to that, ta-da, little review on chirality, okay? The difference between achiral and chiral compounds, okay? I tried to make this as simple as I could on the rules. This is something that's best with practice, not really just memorizing the rules, but what we have here, let's start with chiral, okay? Molecules are either chiral or they're achiral, okay? They gotta be one or the other. We can add meso compounds, but meso compounds are a type of achiral, okay? So chiral compounds have chiral centers. And again, chiral centers, 4 distinct groups, period, okay? So it's gotta have chiral centers somewhere. No chiral centers, out of luck, okay? And there's no symmetry. I think I spelled that right. Don't need to spell great to be a chemist, so helps me out. So there's no internal planes of symmetry. There's no way we can draw a dashed line across that molecule and say this side is the same as that side. Okay, we can't split it in half and say that they're equal. For example, here in the blue, I have cyclopentane with a bromo group, an ether. Okay. Should be able to tell, hopefully, that there's no way I can cut this molecule in half, okay? And both sides are going to be the same, okay? Do I have chiral centers? Is there a carbon on this somewhere where I have 4 distinct groups? Right away, I see this bromine here, okay? I see I have 2 carbon chains, okay, that have different connectivity. This one's reaching my ether group faster. If I go 1 away, 2 away, 3 away, okay, I'm at an oxygen here. So these groups are separate, and then I also have a hydrogen on there. So, boom, there's a chiral center there. Okay. This here would also be a chiral center. Different carbon chains, hydrogen, oxygen on there as well, okay? Multiple chiral centers, at least have 1, no plane of symmetry. There's chiral compounds for you. Achiral, boom, opposite. There's a plane of symmetry I can draw in that molecule here, okay? Okay? Usually no chiral centers, okay? When there are chiral centers, but there is an internal line of symmetry, when there are chiral centers, but there is an internal line of symmetry, that's when we get to meso, okay? Stick with achiral. Plane of symmetry, and there's no chiral centers, for example. No chiral centers, right? Each carbon has 2 hydrogens connected to it, in this case, in our cyclopentane. Because each one has 2 hydrogens on it, the same group, there's no chiral centers. Okay? No chiral centers, achiral. No chiral centers, achiral. Same here. Every carbon has 2 hydrogens on it, achiral. Dashes and wedges, boom, hey, look at chiral center. Nope. Same group, okay? We don't have 4 distinct groups there. Don't be mistaken or, attracted to the wedges and dashes, okay? That doesn't mean that there's a chiral center all the time. This carbon not only has 2 chlorine groups that are the same, but also 2 ethyl groups that are the same, all right? Okay, there's achiral. Meso, kind of in between, okay? Meso is when we do have chiral centers. Notice that these carbons here are both chiral centers, okay? 4 distinct groups on them, but there is an internal line of symmetry. Notice if I look at this and I cut my cyclopentane, my 1,3-dichlorocyclopentane in half, okay? My left side and the right side are the exact same, okay? Write down the central carbon here. That's an example of a meso compound, okay? No chiral centers, achiral, okay? Chiral centers, well, it can be chiral or meso, okay? If there's chiral centers and there's an internal plane of symmetry, it's meso. If there's chiral centers and there's no line of symmetry, I can't split this in half, chiral, okay? I wanted to go over that real quick. It took me a long time to kind of get used to it. When I was a student, this is as simply as I can put it. Dr. Andrews, I hope, can do better. I trust you can. And it's going to take a little bit more practice with that. Hopefully we'll get that Monday in class tomorrow, okay? Just a quick review there. Now, kind of got a little head start on the identifying chiral centers, but go ahead, pause your video, and go ahead and try these 4 examples on your own. Just circle or star where you think the chiral centers are, okay? Welcome back. Glad you paused the video. Great job, okay? Now, I'm gonna go through these quick because you've paused your video and you've had time to look over it. I'm gonna give you more time to make sure I'm still recording. That'd be a bummer. Ah, sweet. Okay. Welcome back again. Okay. Let's go over this real quick. I see, let's go left to right on our top compound. Our first carbon here, notice we have 2 OH groups, not chiral, not a chiral center. Here I have an OH group. I know I have a hydrogen, and my carbon chains, carbon with an OH, actually 2 OH groups, okay? There's a difference there. So I know I have a chiral center, okay? OH, an H group, carbon with an OH, and another carbon with 2 OHs, that's different. 4 groups, chiral center, okay? Here as well, I have an OH group, a hydrogen, these are the same, these are different. 2 OH, and OH, another carbon, chiral center. Do I have 4 distinct groups? Yes, I do. Hydrogen, OH, aldehyde, couple OH groups, long chain there, boom. Here, I'm only bonded to 3 other atoms, not chiral, I need 4 distinct groups, okay? The 3 chiral centers there. Do I have an internal plane of symmetry? I do I? I think you might. I think you can, this way, that's a tough example. Ignore that. We're just doing chiral centers, right? Okay. It's got 3 chiral centers, 100%. Ignore the other part, okay? I'm not starting the video over for that. Okay, let's move on to this one here on the left. Let's identify chiral centers. There's a dash that tells me there's a chiral center. No, okay? Remember, the dashes and wedges are there to just distract you, okay, on this. Just look for the groups. I have a methyl group, I have a methyl group. They're already the same, not a chiral center. 2 methyl groups, the same, not a chiral center. Here I have 2 hydrogens, nope. Here I have a bromine, a hydrogen, okay? Let's look at my carbon chains. Carbons are going same, same, same. Not a chiral center. C with 2 hydrogens on it. C with 2 methyl groups on it. And then we just have our methyl groups there, okay? So notice those tails there are the same. Not a chiral center. 2 hydrogens, not a chiral center. This was the same up here. We have 2 methyl groups, not a chiral center. We have 3 hydrogen groups there. So this one, no chiral center. I really hope you saw all of that. Oof. I think that's in view. Okay, move on here to this cyclic compound. Start with my ketone. I'm bonded to 3 things, not a chiral center. 2 hydrogens, not a chiral center. Bonded to 3 things, no. Bonded to 3 things, no. 2 hydrogens there. Here, I have bromine, hydrogen. These carbon chains are different, okay? This one reaches the ketone faster. This has an alkene in it. This is a chiral center. And then our last example that you've done probably a couple minutes ago because you paused your video and tried it on your own. Too many hydrogens, too many hydrogens, too many hydrogens. Chlorine, hydrogen, methyl group, a longer carbon chain, 4 distinct groups. Here I have an ethyl group, a methyl group, a hydrogen, and whatever this is with a chlorine over here, 2 chiral centers, okay? Our chiral centers is where we can have true stereochemistry and add dashes and wedges that are significant, okay? I can add a dash here, but if it's not on a chiral center, it's not really telling us much, okay? Chiral center practice. Probably gonna do that Monday. Good review, okay? Now, the rest I have went over that review, okay? Wednesday, we're going to be introduced to Fisher projections, okay? Before we get into that, a real quick review of R and S, okay? R and S, just ways that we can describe the stereochemistry of a molecule. When naming molecules, for example, you can add R and S at the very front of the name to designate the stereochemistry. So something like 3-butanol you could have R 3-butanol or you could have S 3-butanol. And that RS configuration would show if that OH group is a wedge or a dash. Okay. This is how I remember it, okay? Our R and S. When I draw an R, okay, I draw it this way, right? Clockwise, the right way. R is going clockwise, and that's the way I draw my R, okay? So when I'm looking at my groups, I'm going clockwise in my priority, okay? And S, okay, is the opposite. It's counterclockwise, S for sinister, or the other way, left-handed, okay? We're going counterclockwise, okay? I was pretty proud of this diagram. I thought of that on my own, okay? So, not a big deal. And then, okay, once we have our R and S configuration, when our lowest priority group, doesn't have to be a hydrogen. I drew hydrogen here. It's usually hydrogen. 9 out of 10 times it's going to be hydrogen. But whatever our smallest priority group is, whatever our smallest atom or chain, when it has a wedge, okay? When it has a wedge, you need to flip that R and S orientation. Meaning, if it was R when you went through your groups, but that hydrogen is in a wedge, that means your R is now an S. All you do is just flip it, okay? When you see this, a wedge to your smallest group, usually a hydrogen, just flip R to S, S to R, okay? Again, we just use those for naming conventions, and we can talk about different molecules based on stereochemistry.